This is a problem about a communication satellite orbit. Communication satellites are placed in a geosynchronous orbit, that is a circular orbit such that they complete one full revolution about the Earth in one sidereal day. That's 23.394 hours. These communication satellites in a geosynchronous orbit appear stationary with respect to the ground. So you can point your satellite TV antenna at a certain place in the sky, and the satellite will always be there. That's a geosynchronous orbit. So the questions are: determine first the altitude of these satellites above the surface of the Earth, and second, the velocity with which they orbit. We solve this problem the same way we solve all these problems. We start off with the sum of all the forces is equal to the mass times the acceleration. Now in this case we're talking about a circular motion. It's a circular orbit, so the acceleration we will write as the velocity squared divided by the radius. We'll set this tau to be the period of the orbit. That's 23.394 hours. And what do we know about tau? Well, if we take the velocity times the period of the orbit, that's the velocity it's going times the amount of time it takes to go in a single orbit, that should equal the circumference of the orbit. That's 2 pi times r. So we have an expression here for the velocity. In this case, we've got 2 pi r divided by the tau. We've got an expression up here. In this case, velocity is going to be gm over r. And let's set these two equal and solve for r. So we have that 2 pi r divided by the period tau has got to equal gm divided by r. We can solve for r. The easy way to do this is to first square each side. So we've got this 4 pi squared r squared divided by tau squared equals gm divided by r. And you can see so this ends up being r cubed equals gm times the period squared divided by 4 pi squared, or r equals the 1/3 power or cube root of gm tau squared divided by 4 pi squared. Okay, there's our expression for r. We had an expression for v up above. Let me rewrite that. Once we figure out r, we'll just have v here is 2 pi r divided by the period. We know the period, that's this value here. We know these. G is the universal gravitational constant. M is the mass of the Earth. The period here. So we can calculate r and then bring it over here and calculate v. And so we can complete the problem. Now I'm going to do the calculation. I'll use Wolfram Alpha to do the calculation. Here it is. So we can just, Wolfram Alpha is smart enough, we can just type in a day in seconds. And so then we know there's how many seconds we need, 86,164. We'll go back to Okay, there's the time in seconds for the period, and we need the mass of the Earth and the gravitational constant, so we'll put those in. Now, so I've typed it in here, g times the mass of the Earth times the sidereal days squared, and then that divided by 4 pi squared, and then the whole thing to the 1/3 power. You can see Wolfram Alpha says it's assuming the gravitational constants for g, and that's what we want. And so here's the interpretation of the input, and that's what we want. And so there's the result, 4.217 times 10 to the 7th meters, the equivalent of 26,200 miles. And you can see all these comparisons it puts in here. So one interesting one is the light travel time in a vacuum. So it's 141 milliseconds it takes to travel from the center of the radius, to the geosynchronous satellite. And so there we go. We've calculated the radius is equal to 4.217 times 10 to the 7 meters. Is that the answer? Well, let's see. What was the question again? Let's go back up here. The question was the altitude above the surface of the Earth. Now we've calculated here. Here's what we've calculated. We've got something like this is the Earth. Here's our orbit like this. And the question is asking for this distance here, the altitude above the surface of the Earth. We've calculated a different distance all the way to the center of that circle. So we have to subtract the radius of the Earth from this. So we'll say this, the altitude is equal to r minus the r we've just calculated, the radius of the Earth. Or you can go and look that up, and that is so I've added that into the Wolfram Alpha thing. I said minus the radius of the Earth. It calculated this. You can see the input interpretation. Here's what we want, minus the Earth's average radius. The Earth is not exactly a sphere, so they'll calculate the average radius, and here's the result, 22,250 miles, or 35,800 kilometers. And there's our answer in kilometers. Now the second question, the velocity in Wolfram Alpha also. So let's just write it down. It's the square root of g times the mass of the Earth divided by the radius, which we've previously calculated. Remember, the radius, not the altitude, but the radius was worked out to be about 145 kilometers. And so that should be it. Let's see what we get. Okay, 3,076 meters per second. And here's some comparisons. There's in miles per hour. And actually, so we're almost exactly what they have is the orbital speed of geostationary orbit. We're a bit off just from rounding errors. Okay, so let's write that down. It's 3,076 meters per second.